cyclic stress strain curve. The stress strain response of a material is different when it is cyclically loaded when compared to monotonic stress strain curve. It depends upon the initial condition of that material, whether it is cold worked or it is annealed. In the case of cyclic stress strain behavior, one is maintaining the strain amplitude constant, and second is maintaining the stress amplitude constant. For the case of stress amplitude constant, maintaining the stress amplitude constants, this stress amplitude depends upon the applied or the specific loads for the case of constant stress amplitude. It depends upon the external loads, whereas for the case of constant strain amplitudes, the loads and strains are from the difference in variations or the difference in temperatures or variations in temperatures. Cyclic stress strain behavior. The stress strain behavior, it changes when a material is subjected to cyclic loads. It depends upon the initial condition of that material, whether it is cold worked or whether it is annealed. Stress control loads occur if the loads are specified by external loads, and for the case of strain control loads, they occur if there are variations in the temperatures. So, due to the variations in the temperatures, thermal stresses develop in the material and causes thermal strains. So, this stress controlled fatigue loading or strain controlled fatigue loading, it depends upon the stresses that are employed. Either the stresses are decided by the external loads in the case of stress controlled fatigue, or in the case of strain controlled fatigue, where the stresses originate from the thermal means. The origin of stresses is by thermal, where in the case of stress controlled fatigue, the origin of stresses is by mechanical means. So, some of the components which are subjected to very high temperatures, if there are variations in the temperature, the component, it is not allowed to expand and contract freely because of the restraints. Thereby, thermal stresses are developed in that material, which gives rise to thermal strains. So, stress controlled fatigue loading, it is somewhat similar to that of high cycle fatigue, and strain controlled cyclic loading is equal to that of low cycle fatigue. But this is not a rule that all stress controlled loading are of high cycle fatigue, and cyclic stress strain curve. The stress strain behavior, it changes. The stress strain behavior of a metal, it changes during cyclic loading. It depends upon the initial condition of the material. Stress controlled fatigue loads occur if the loads are specified by external loads, and strain controlled loading occurs if the loads are due to thermal origin. That means if a component it is subjected to very high temperatures, due to variations in the temperatures, due to some changes in the temperatures, stresses are induced in that material, because at high temperatures expansion of the material takes place, low temperatures contraction of the material takes place. So due to variations in temperatures, expansion and contraction occurs, and the material it is not free to expand or contract, it is restrained. So because of the constraints, the material is not allowed to expand freely and contract freely, thereby thermal stresses are developed in that material. So the strains are due to the thermal origin. Most often the stress controlled loading comes under high cycle fatigue, and strain controlled loading comes under low cycle fatigue. But this is not a rule that stress controlled loading it is equal to that of high cycle fatigue, it comes under high cycle fatigue, and strain controlled loading it comes under low cycle fatigue. But this is not a rule. Mostly it is observed that for the case of stress controlled loadings, it is quite similar to that of high cycle fatigue and that of the low cycle fatigue, where the strains are very high. They are in the strains are in the plastic regime, the stresses are in the plastic regime. So strain controlled loading comes under low cycle fatigue, but it is observed mostly, and this is not a rule. Now we see the stress strain behavior of a material during cyclic loading. Stress strain behavior of a material during cyclic loading. Cyclic stress strain curve. Plastic deformation is not completely reversible, so the stress strain response of a material is complex during cyclic loading. Consider a material where it is loaded from the initial point O to the point A, and the component at point A it is unloaded to point D, where at this point D the material does not experience any stress, and from point D to the point B it is loaded in compression. At point B the compression is relieved, and then the material again it is reloaded in tension. When it is reloaded in tension, this is the path for the material. So A to D we have unloading, we have loaded from the point O to A. A to D is the unloading. Again from D to B we have applied compressive forces. Then again from B, C, A, where the component is subjected to tension. So OA, the component is subjected to tension. Point D, where the component has experienced no stress, and AB, the component is subjected to compression, and again from B to A the component is subjected to tension, and again at the point C the component experience no stress. Points A and B represents the stress and strain limits. These points A and B represents the stress and strain limits. So this is the total stress range. This is stress versus strain behavior under cyclic loading. So this is the total stress range, and this is the total, this points corresponds to the total strain range. This total strain range comprises of two components. Total strain range comprises of both elastic strains and plastic strains. So, these points corresponds to, this is the point B. So, this is the plastic strain range and this is the elastic strain range. Together constitutes the total strain range, where this is the elastic strain range, that is delta sigma by E, and this is elastic strain range delta sigma by 2E. Within the elastic regime, stress is proportional to strain by proportionality constant, that is the Young's modulus. When the strains are plastic, when the stresses are in the plastic regime, plastic strains are induced in the material and the stress strain response of a material is complex. So, this is a hysteresis loop which shows the total stress range, total strain range, which comprises of both plastic strain and elastic strain. The width of the loop at its center is the plastic strain, that is CD. So, the width of the loop at its center is the plastic strain. So, the area within this hysteresis loop is equal to the energy loss or work done per cycle. So, this cyclic stress strain behavior of a material under cyclic loading is quite different from that of monotonic behavior of a material when a component is subjected to monotonic stress. So, now we will discuss about the two types, that is, one is strain controlled cyclic loading and the second one is stress controlled and strain controlled cyclic loading. In the case of strain controlled cyclic loading, the strain amplitude it is held constant, and in the case of stress controlled cyclic loading, the stress amplitude it is maintained constant. So, the strain controlled cyclic loading it is seen for the components which are subjected to large variations in temperatures. Example for the cases of nuclear pressure vessels, some components of power machinery, etc. So, when there are very large variations in temperatures, stresses are developed, thermal stresses are developed and causes thermal strains. So, in the case of constant strain amplitude, the behavior of a material it depends upon the initial condition. If the initial condition of the material is cold worked and this cold worked material it is subjected to strain controlled cyclic loading, then the material will undergo cyclic softening. If the initial condition of the material is annealed and it is subjected to constant strain amplitude cyclic loading, then the material will undergo cyclic hardening. So, this by means of the figure you can visualize the cyclic softening and the case of cyclic hardening in the case of constant strain amplitude, that is strain controlled cyclic loading, strain controlled cyclic loading. So, the left side is the strain control, the parameter that is held constant, which is the strain amplitude that is held constant, strain amplitude with respect to time. And on the right side, I draw the figure for the behavior of a material when this parameter is maintained constant, that is when strain amplitude is maintained constant. This is the stress amplitude and with respect to time. For the case of material which is initially cold work, that means initially the material is hard, if it is subjected to cyclic loading under constant strain amplitude, then the material will undergo softening. So this is the response of a material, initially hard material, a cold worked material, when it is subjected to constant strain amplitude cyclic loading. This is the parameter which is maintained constant, and this is the behavior of a material. And this is the cyclic stress strain curve. This is the cyclic stress strain curve. So initially the material is hard. Initially the material is hard because it is being cold work. Due to strain hardening, the material is stronger. So when this material is subjected to cyclic loading under constant strain amplitude, so this is 1, 2, 3. Four, five. So this is a plot of stress versus strain behavior under cyclic loading. The strain is maintained, strain amplitude is maintained constant, and you can see this is the initial loading path where the material is subjected to initial loading 0 to it is loaded to this point. Next, upon cyclic loading, this is 2, this is 3 and 4. This indicates that the stress required to maintain the same strain range decreases for the case of a harder material or for the case of cold work material. So the stress required to maintain the same strain range, it is decreased. That means the material has undergone cyclic softening. So this is for the case of stress strain response of a material under cyclic loading, strain controlled cyclic loading, where the material has undergone cyclic softening. Next, for the case of a soft material, that is for the case of annealed material, when it is subjected to strain controlled cyclic loading, again the parameter that is maintained constant is strain amplitude, which is maintained constant. So this is the strain amplitude which is maintained constant. The response of a material, stress amplitude with respect to time. The material undergoes hardening. So, this is the material answer for a case of soft material, annealed material, when it is subjected to strain controlled cyclic loading. That means the stress amplitude, it increases. To maintain the same strain range, the stress amplitude increases. So, the material undergoes hardening, that is cyclic hardening, during the cyclic loading. So, this is the stress strain behavior for the case of soft material. Initially it is loaded, this is O, this is 1, first point. So, this is 1, 2, 3, 4 and 5. So, this is 1, 3, 5. Here a number indicates the cycle. This is the initial cycle here, the first cycle, and upon cyclic loading the stress amplitude, it has decreased, and here the stress amplitude, it has increased. So, this is for the case of a soft material which undergoes cyclic hardening. The reasons why a material shows this type of cyclic softening or cyclic hardening, it depends upon the dislocation microstructure. So, depending upon the initial condition of the material, it either goes cyclic softening or cyclic hardening, or it remains stable. So, after some few hundreds of cycle, this cyclic stress strain curve, it reaches to saturation, that means it is stabilized. The stress amplitude reaches a saturation, that means the component reaches to a saturation. There is no further increase in stress amplitude. After some few hundreds of cycle, this curve stabilizes and reaches to a saturation point. So, the reasons for the case of why cyclic softening or cyclic hardening occurs in the case of cyclic loading, it can be related with respect to that of dislocation microstructure. For the case of a cold work material, or for the case of a material which is very harder, the initial condition of the material is it has been deformed, it has been cold worked. So, when the material, it has given some amount of cold work, strain hardening occurs, mainly due to the dislocation, number of dislocations increases during plastic deformation. The density of dislocation is high for the case of a strain hardened material or the cold worked material. Upon cyclic loading, the dislocations, they rearrange into more stable network, or annihilation of dislocation takes place and their number comes down. Thereby the material undergoes softening, that means the stress amplitude, to maintain the same strain range, it decreases during cyclic loading. And for the case of a soft material, an annealed material, initial condition of the material is an annealed one. When this material, it is subjected to cyclic loading, for an annealed material, the number of dislocations or the dislocation density is lower, it is quite low. So, when this annealed material, it is subjected to cyclic loading, the dislocation density will increase during plastic deformation. Number of dislocations will increase, and this leads to strain hardening, that is the strength of the material increases. So it undergoes cyclic hardening during the cyclic loading. The stress amplitude increases during cyclic loading. So this is about the strain controlled cyclic loading, and the parameter that is held constant, and this is the material answer, how a material is subject, how a material responds to the strain controlled cyclic loading. So depending upon the initial condition, it may undergo either cyclic hardening or cyclic softening, and this is the stress strain response for that material. So this loop, it gets stabilized after a few hundreds of cycles. It reaches to saturation. For the case of stress controlled cyclic loading, where the stress amplitude, it is maintained constant, it is held constant, stress amplitude is held constant. This is a parameter that is maintained constant. And this is the material answer, that is strain amplitude, it varies strain amplitude varies, where stress is maintained constant, and the cyclic stress strain curve, it shifts along the strain axis. So this is the cyclic stress strain behavior for a material where the stress amplitude is maintained constant. The hysteresis loop, it shifts towards right along the strain axis. The stress amplitude, it is maintained constant. So this is known as ratcheting. So this is for the case of stress controlled cyclic loading. So again, the reasons can be attributed to that of dislocation microstructure in the case of stress controlled cyclic loading. So for the case of strain controlled cyclic loading, this is a comparison which shows for the case of strain controlled cyclic loading and with the of a monotonic stress strain curve. So both the graphs are superimposed, both the curves are superimposed. That is for the case of strain amplitude which is maintained constant for the case of cyclic loading and for the case of monotonic stress strain curve. Monotonic stress strain curve. So when this both the graphs are superimposed, so this dotted line, this line, this curve indicates the monotonic stress strain curve. This is for the case of monotonic. So these points here indicates the stress amplitudes in the case of constant strain amplitude test. These are the points that indicate the constant value of stress amplitudes, constant value of stress amplitudes. So this constant value of stress amplitude occur after a few hundreds of cycles where the hysteresis curve it stabilizes, the stress amplitude reaches to saturations. So those points are taken and these are plotted with respect to the strain amplitudes. Initially a particular strain amplitude, a constant strain amplitude is taken and the component is subjected to cyclic loading. So depending upon cyclic hardening or cyclic softening, the material undergoes this hysteresis loop. The strain amplitude keeps on increasing or decreasing. After some few hundreds of cycle, the curve stabilizes and reaches to saturation. So that saturation point, the point at which the curve stabilizes, are the saturated value of the stress amplitude. It is taken for the specific strain amplitude and then it is plotted in this stress strain curve. Similarly, for the second experiment where the strain amplitude is different, the constant strain amplitude, the material is subjected to cyclic loading and again this after few hundred cycles the material undergoes saturation where the stress strain behavior, cyclic stress strain behavior, that is the hysteresis loop, it stabilizes. So that point again the stress corresponding stress amplitude is taken. So these points are joined, that is the peaks of the hysteresis loops where the curve stabilizes, those points they are joined with respect to this strain amplitudes. And so this is the cyclic stress strain curve. This is the cyclic stress strain curve and this is the monotonic stress strain curve. So both this cyclic stress strain curve and monotonic stress strain curve do not coincide. Either monotonic stress strain curve, it lies above this cyclic stress strain curve or it lies below the stress strain curve, the cyclic stress strain curve. It depends upon whether the material undergoes a cyclic hardening or cyclic softening. If the material undergoes cyclic hardening, then the cyclic stress strain curve it falls above that of, it is above that of monotonic stress strain curve. If for the case of cyclic softening, then this cyclic stress strain curve it is below that of monotonic stress strain curve. In this case here the monotonic stress strain curve it is below that of cyclic stress strain curve. It means that the material has undergone cyclic hardening. So this is the example for the case of cyclic hardening. So this is the comparison between the cyclic stress strain curve and that of monotonic stress strain curve. So this cyclic stress strain curve it can be approximated by means of an power curve equation which is similar to that of the power curve equation for the case of true stress versus true strain curve within the region of uniform plastic deformation. So here the cyclic stress strain curve can be represented as delta sigma, it is the stress amplitude is equal to K prime into delta epsilon P whole to the power of n prime, where delta sigma is a stress amplitude, delta epsilon P is the plastic strain, and K prime is cyclic strength coefficient, and n prime is cyclic strain hardening exponent. So the total strain range comprises of two components. In the case of the cyclic stress strain curve, it is equal to elastic strain plus that of the plastic strain component. So within the elastic regime, stress is directly proportional to strain by means of a constant, that is the Young's modulus. So this can be approximated as delta sigma by 2 by 2E plus delta epsilon P. It can be obtained from this power curve equation, that is equal to delta sigma by K prime whole to the power of 1 by n prime. So this is for the case of the total strain range, which comprises of both elastic and plastic, where K prime is the cyclic strength coefficient and prime is cyclic strain hardening exponent. So a material, whether it undergoes cyclic hardening or cyclic softening, it depends upon the initial condition, as well as if the ratio of ultimate tensile strength, the monotonic ultimate tensile strength, to that of yield strength, if it is greater than 1.4, if this ratio of ultimate tensile strength to the yield strength is greater than 1.4, then the material will undergo cyclic hardening. And if this ratio ultimate tensile strength to the yield strength, if it is less than 1.2, then the material will undergo cyclic softening. It undergoes cyclic softening. So the cyclic hardening and cyclic softening, it can also be related with respect to the strain hardening, monotonic strain hardening exponent, that is n. So n is for monotonic strain hardening exponent and n prime is for cyclic strain hardening exponent. If n is greater than 0.12, then the material will undergo cyclic hardening. If n is less than 0.12, then the material will undergo cyclic softening. have discussed about the high cycle fatigue, where the stresses are well below the elastic regime and the number of cycles to failure is very high. It is about the order of greater than 10 to the power of 5. Now, we shall discuss about the low cycle fatigue, where the stresses are high above that of the elastic regime and the number of cycles to failure is low, it is less than 10 to the power of 5 cycles. So, the origin of stresses in the case of low cycle fatigue is mainly from the thermal origin, whereas in the case of high cycle fatigue it is by means of mechanical means. So, most of the components in the high temperature applications, they are subjected to repeated thermal cycling because of variations in temperatures, due to which thermal stresses are developed, because the component is not free to expand and contract freely. Thereby strains are induced in that material, thermal stresses are induced and causes thermal strains. So, this low cycle fatigue, it is a plot of log coordinates of plastic strain range versus number of cycles to failure, where the number of cycles to failure, it is less than 10 to the power of 5. So, when a log plot of plastic strain range versus number of cycles to failure, it is plotted, it results in a straight line. So, the equation, it is given by Coffin-Manson equation, whereas in the case of high cycle fatigue, the equation, it is given by Basquin equation. So, in the case of low cycle fatigue, it is a plot of plastic strain range versus number of cycles to failure. It results in a straight line. So, this low cycle fatigue, it is given in the form of equation which is given by Coffin-Manson plastic strain range delta epsilon p is equal to epsilon prime f into 2n whole to the power of c, where C is a constant, that is equal to, C has the values of about 0.52 minus 0.7 minus 0.52 minus 0.7, and delta epsilon p is plastic strain range, epsilon prime f is fatigue ductility coefficient, which can be related to that of fracture strain in case of monotonic tensile strain. So, this is fatigue ductility coefficient, which can be related, which is equal to that of true fracture strain in the case of tension test, and 2n is number of reversals to failure, where one cycle corresponds to 2 reversals. 2n is number of reversals, where one cycle is equal to 2 reversals. So, low cycle fatigue, the number of cycles are low and the stresses are higher. and where in the case of high cycle fatigue, the stresses are low, the strains are low, and the number of cycles to failure is high. So combining both the low cycle fatigue and that of the high cycle fatigue, one can get an equation which represents the total life of the component, that is total strain life of a component when it is subjected to cyclic loading. So the Basquin equation which is for the case of high cycle fatigue, where the stress amplitude is equal to, it can be related to that of elastic strain, this is equal to sigma f prime into 2n whole to the power of b, where sigma f prime is fatigue strength coefficient, it is fatigue strength coefficient obtained at a value of strain intercept 2n is equal to 1, and b is fatigue strength exponent, where in the case of low cycle fatigue, Coffin-Manson equation, C is fatigue ductility exponent, it is fatigue ductility exponent, it has the values of minus 0.5 to minus 0.7, where in the case of Basquin equation, which is related to high cycle fatigue, the stress amplitude is equal to elastic strain into the Young's modulus, because here the strains are within the elastic, the stresses are within the elastic regime, and this is equal to sigma f prime, that is fatigue strength coefficient, 2n is number of reversals, where one cycle is equal to 2 reversals, and b is fatigue strength exponent, which has values of about minus 0.052 minus 0.12. So combining these two equations, we can get the total, that is the total strain range is equal to the sum of both the elastic component and that of the plastic component. So it gives an equation which gives information about the total fatigue life. So combining these two equations, we have combining this Basquin equation and that of the Coffin-Manson equation, both the high cycle and low cycle fatigue, we have epsilon f 2n whole to the power of c plus sigma f prime by E into 2n whole to the power of b. So this is for the case of total strain range. We have a combination of both, sum of the high cycle fatigue and that of the low cycle fatigue equation, combining the Basquin and Coffin-Manson equation. So one can estimate the life of a component. One can estimate. So combining these two equations, one can estimate the fatigue life of a component for the case of both a combination of high cycle and that of the low cycle fatigue. So from this equation we have delta epsilon by 2 is equal to delta epsilon E by 2 plus delta epsilon P by 2, that is equal to, we have sigma f prime by E into 2n whole to the power of B plus epsilon f prime into 2n whole to the power of C. So this equation is also known as strain life equation. A smaller value of C results in, if the value of C is low, it results in increase in fatigue resistance, increase in fatigue life, and a smaller value of B, it results in higher fatigue life. It results in high fatigue resistance or high fatigue life. B and C, they are related to N prime, which is known as cyclic strain hardening exponent. Cyclic strain hardening exponent. So C is equal to minus of 1 by 1 plus 5 N prime, and B is equal to minus of N prime by 1 plus 5 N prime. So in the case of Coffin-Manson equation, lower the value of C, greater is the fatigue resistance of that material, greater is the fatigue life of that material. So C and N prime are related with respect to this equation. So a larger N prime results in increase in fatigue life or fatigue resistance. whereas the equation which is governed by Basquin equation, B is related to n prime by this equation. So a smaller value of n prime results in increase in fatigue life for the equations governed by Basquin equation, and this is for the equations governed by the Coffin-Manson relation. So smaller value of C and smaller value of B results in increase in fatigue resistance, but C and B are related to n prime by these equations. So for the case of Coffin, when the Coffin-Manson equation is obeyed, a higher value of n prime results in increase in fatigue resistance, and when Basquin equation is obeyed, then a smaller value of n results in increase in fatigue resistance. Manson has proposed a simplified version of this strain life equation, which is known as method of universal slopes. So that is given by this equation. (3.5) times of ultimate tensile strength by Young's modulus into 2n whole to the power of minus 0.12 plus epsilon f power 0.6 into 2n whole to the power of minus 0.6. So this is known as method of universal slopes, where the fatigue strength coefficient, it is related to the ultimate tensile strength for the case of tension test, and fatigue ductility coefficient is related to true fracture strain in the case of tension test. So this is known as method of universal slopes. So this is known as the strain life equation, which gives the entire fatigue life, and this can be plotted by means of a graph where both the plastic and elastic curves are plotted, and the total fatigue life of the specimen is plotted. This is the plastic and this is the elastic curve. The slope of this elastic is B and slope of this plastic is C. Where this is for the case of total life, combination of both high cycle and low cycle, and this is the elastic curve and this is the plastic curve. This is the total strain range and this is the number of reversals. So this strain life curve, which is a combination of both high cycle fatigue and low cycle fatigue, it tends towards the plastic strain amplitude. For this, it tends towards this plastic curve, the strain life curve, it tends towards the plastic curve for high values of strain amplitudes, and for the values of low strain amplitudes, this strain life curve, it tends towards the elastic curve. For high strain amplitudes, the strain life curve is towards, it tends towards the plastic, and for the case of low strain amplitudes, the curve tends towards the elastic curve. And at this point, the transition occurs. So transition is given by 2nt is equal to epsilon f into E by sigma f prime whole to the power of 1 by B minus C. So this is where the transition occurs. It is given by this equation, epsilon f prime into E by sigma f prime whole to the power of 1 by B minus C. So from these equations, it can be understood that high ductile materials show better resistance to fatigue for the case of low cycle fatigue, and stronger materials have better fatigue resistance when they are subjected to high cycle fatigue. High cycle fatigue, which is low strain fatigue, and low cycle fatigue, which is high strain fatigue. So ductile materials are preferred for low cycle and strong materials are preferred for high cycle. For overall fatigue resistance, tough materials are preferred. Now, fatigue crack nucleation and growth. Fatigue cracks, they generally initiate at the free surface. If there are any notches present on the surface, roughness of the surface, discontinuities of the surface, all these leads to the initiation of crack at the surface. Fatigue crack can also generate interior if there are certain discontinuities, porosity, etc. So even though if there are no discontinuities present or no notches present on the surface, still the fatigue crack initiate at persistent slip bands. Persistent slip bands means these slip bands, they cannot be eliminated by repeated polishing. Even though by repeated polishing and etching, these slip bands, they still persist. So the name persistent slip band. They are due to systematic build-up of fine slip movements of order of 1 nanometer. So because of this fine slip bands, the persistent slip bands, fatigue crack nucleates at the persistent slip bands, which leads to intrusions and extrusions. At this point, the fatigue crack nucleates. So the plastic deformation within this persistent slip band, it is 100 times greater than that of the surrounding regions. So this leads to intrusions and extrusions where the crack nucleates. So there are 3 stages for the initiation, propagation and final failure. Initiation of cracks, propagation of cracks and eventual failure takes place. Stage 1 is for the initiation of fatigue crack. Stage 2 corresponds to the fatigue crack propagation, and stage 3 occurs when the cross section of the material, it can no longer withstand the applied stress. It leads to failure. So as discussed now, these fatigue cracks, they initiate mainly at the surface, at the external surface, free surface. Even though there are discontinuities or notches or flaws present or not on the surface, still they can initiate at persistent slip bands, PSBs. because they can persist even after repeated polishing, so the name persistent slip bands. So once the fatigue crack nucleates, it propagates and it leads to failure. Now we shall see the different stages in the case of fatigue crack initiation and propagation. The first stage corresponds to stage 1 is the fatigue crack initiation stage, where the crack initiates at the slip bands due to the formation of intrusions and extrusions. So this is the slip plane. Due to the back and forth movements, it leads to intrusions and extrusions. So this is back and forth movement which leads to an extrusion. So the crack nucleates, initiates at these intrusions and extrusions. So this is a figure which shows the slip band intrusions and extrusions, where the crack initiates, even though there are no notches or surface defects present. Still there is a possibility for the crack to initiate at the persistent slip bands. So this is the intrusion and this is the extrusion, which occurs due to the back and forth movement of the slip bands. So this is the back and forth movement which creates this intrusions and extrusions. So these are the places where, regions where the crack initiation takes place. Initially, in the case of stage 1, the crack propagation is very, very slow. Once the crack initiates, nucleates, the propagation, the growth of the crack is very, very slow and is essentially a featureless for the case of stage 1. Once the crack nucleates and it grows in size, then the crack changes its direction. Initially, the crack, it grows, it propagates along the direction of the slip bands, along the slip bands, which are about 45 degrees to the principal tensile axis. So this is the initial, if this is a material, initially the crack propagates in a direction which makes an angle 45 degrees to that of principal tensile axis. The crack grows along the slip bands which are at an angle of 45 degrees to the principal stress direction. once the crack reaches to a sufficient length, the stress magnitude at the crack tip, it reaches to a sufficient value, it reaches to a high value to become dominant, and then the crack changes its direction, of propagation, and then it enters into stage 2, where the crack grows in a direction perpendicular to the principal tensile axis. So this is the stage 1, where the growth of the crack is 45 degrees to the principal tensile axis, and this is the stage 2, where the crack is the stage 2, and this is stage 1, where the crack changes its direction, which is perpendicular to the principal tensile axis, and it propagates. So in the case of stage 2, striations are observed. Each striation, it is approximately equal to 1 cycle. These striations, they are the characteristic of the material that has failed by fatigue. It is the characteristics of fatigue failure. Even though if striations are not present, it doesn't mean that the material has not failed by fatigue. So these striations, they are seen for the case of a ductile material, where for the case of very high strength materials, striations cannot be observed. And these striations, they cannot be seen by means of a naked eye. They can be observed by electron microscope, by scanning electron microscope, where one can observe the striations, which are indications that the material has failed by fatigue. So finally, these striations, they lead to the concentric markings, which are known as beach marks. Each concentric marking, it is approximately equal to that of some thousands or tens of thousands of cycles. So these concentric rings can be visualized, whereas striations, they have to be visualized only by means of, they can be seen only by means of an electron microscope. So this is the stage 1, where because of the formation of persistent slip bands, the crack initiates at the persistent slip band, even though there are no defects present on the surface of the material. These slip bands, due to the backward and forward movement, back and forth movement of the slip bands, leads to intrusions and extrusions, and they create a rough surface where the crack nucleates, and the propagation in stage 1 is very, very slow and is essentially featureless. Once it reaches to sufficient size, then it changes its direction and enters into stage 2, where the crack propagates by a series of blunting, sharpening, blunting and resharpening. And in the third stage, the material cross section is not sufficient to bear the stress. The material cross section has reduced to such an extent that it is unable to withstand the load, and finally the material undergoes fracture, failure by fatigue. So in the stage 2, this is stage 1, and stage 2, where the crack propagates, striations are observed in the case of stage 2. The crack propagates by a series of blunting and sharpening. So this is the figure. This is the spacing between the striation. This is the crack within the material. This is A. So, when this is subjected to cyclic loading, crack blunting, resharpening takes place. So, blunting and resharpening takes place. This is A, this is B, C, So, these are the figures which indicates the crack propagation in stage 2. This is the spacing between the striations, where during the cyclic loading, crack blunting, resharpening, blunting, resharpening. This is the crack blunting takes place here. Again the crack undergoes resharpening to propagate. Again crack blunting has taken place, and finally the crack advances by this series of blunting and sharpening in the case of stage 2, where striations can be observed. Next, in the case of stage 3, where the material cross section has decreased to such an extent it cannot withstand the stress and finally leads to failure. Now, what is the effect of stress concentrations during this cyclic loading? So, stress concentrations, as we have already discussed in the case of tension test, where these stress concentrations which are induced as a part of design, example like keyways, threadings, so they create stress raisers, that means they act as stress raisers, they concentrate stress, and there exists a triaxial state of stress. So, these are the three effects of notches. So, for the case of fatigue, the fatigue strength or fatigue life is lowered due to the presence of this stress concentrators. So, fatigue strength of a material for the case of this, when stress concentrators are present in the specimen, it can be evaluated by testing a notched specimen. By comparing the SN curve, stress versus number of cycles to fatigue curve, for notched specimens and unnotched specimens, one can assess the fatigue life of a component in presence of this stress concentrators. This stress concentrators can be due to design induced features like the keyways or the threads, or else they may be induced during the manufacturing process like the surface roughness and the residual tensile stresses. So, these also act as stress concentrators. So, during manufacturing process, if the applied stress is compressive, then it leads to residual tensile stress on the surface, so which lowers the fatigue life of the material. So, fatigue life can be assessed by comparing the notched and unnotched specimens from the SN curve. By testing a notched specimen and unnotched specimen and comparing the SN curve for these specimens, one can assess the fatigue life in presence of this stress concentrators. So, fatigue life is reduced in presence of this stress concentrators. So, the reduction in fatigue life due to the stress concentrators is known as fatigue strength reduction factor, which is indicated by the symbol K subscript F, stands for fatigue strength reduction factor. Or which is also known as fatigue notch factor. So, this fatigue strength reduction factor or fatigue notch factor, it is given by Kf, that is the ratio of fatigue strength in presence of notch, fatigue strength for the case of unnotched specimen to that of fatigue strength in the case of notched specimen. Fatigue strength reduction factor or fatigue notch factor, it is the ratio of fatigue strength in the case of unnotched specimen to that of fatigue strength for the case of notched specimen. So, this Kf can also be related to fatigue strength and notch to that of fatigue strength notched. This can also be related to a factor Q, which is known as notch sensitivity factor, which is notch sensitivity, that is indicated by small q, which is equal to Kf minus 1 by Kt minus 1. So, notch sensitivity is related to fatigue notch factor, and where Kt is theoretical stress concentration factor, which is given by sigma maximum by the sigma nominal stress, that is sigma nominal, maximum stress at the vicinity of the notch to that of the nominal stress. So, Kt. So, for the case of Kf equal to 1, that is when there is no reduction in fatigue strength due to the presence of a notch, means the strength of the material, fatigue strength has not reduced due to the presence of a notch, then fatigue strength for unnotched specimen is equal to fatigue strength for notched. Kf is equal to 1. When Kf is equal to 1, we have Q is equal to 0. That is, for Kf is equal to 1 when there is no effect of notch on fatigue strength, and Q is equal to 1 for the case when Kf is equal to Kt. That means the fatigue strength has reduced in presence of a notch, and it has reached to the theoretical value, theoretical stress concentrated value, that is Kt. Kf is equal to Kt. Then we have Q is equal to 1. This is the case when Kf is equal to Kt. So, this Q, it is quite sensitive to the notch radius. So, Kf, it depends upon the stress level, as well as it depends upon the material, it depends upon the shape of the notch, and it depends upon the severity of the notch. Q is sensitive to the notch radius, notch root radius. Q is sensitive to notch root radius. Q is low, the Q value is low when this notch root radius is low. When this notch root radius is low, because Kf increases more slowly for small radii notch when compared to Kt. Kt increases to a greater extent when compared to Kf. Kf, it increases more slowly as the notch root radius decreases. Thereby, Q is low for the notch radius is low. Kf, it increases with respect to the notch radius. Kf increases with increase in notch radius, but with decrease in notch radius, Kf increases very slowly when compared to that of Kt. Thereby, the value of Q is low. For notches with greater radius, when the radius of the notch is greater, for large radius notch, for the large radius notch, Kf is equal to Kt, but for the case of small radius notch, Kf is less than Kt. Thereby, Q is low for low radius notch. So, this is the effect of stress concentrators in the case of fatigue. And moreover, low strength materials, they are less sensitive when compared to high strength materials. Or in other words, we can say that low strength materials are less affected when compared to high strength materials because of the limited capability of deformation. High strength materials are more affected by these stress concentrations because of the limited capability of deformation for high strength materials and large increase in the plastic zone at the crack tip. High strength materials are more severely affected by the stress concentrators than when compared to low strength materials or high ductile materials. Now, the next topic in fatigue is cumulative damage rule, which is given by Palgram Minor, which is also known as Minor's rule. It is cumulative damage. So, in the case of cumulative damage, fatigue tests, they are conducted for the case of simple conditions, for the case of constant amplitude and at constant frequency. Tests are conducted for the simple conditions by maintaining constant amplitude and constant frequency. But this is not the same in real applications. Most of the applications, the conditions are more complex. The loads are not as simple. There is a large variations in the fluctuation stresses, in the fluctuating stresses, a large range of mean stress levels, a large range of stress ratio, as well as the frequency is also a variable. So, under these conditions, one can predict the life of a component at variable amplitudes and variable frequencies from the data generated from the tests conducted at constant amplitude and constant frequency. That means one has to predict the life of the component which is subjected to variable amplitude and variable frequencies from the data obtained from the tests which are conducted at constant amplitude and constant frequency. So, this damage rule, which is also known, which is given by the scientist Minor, Palgram Minor, which is known as Minor's rule, it assumes that fatigue damage is accumulated till the life of the component is exhausted. That means it is a damage accumulation process until the life of the component is exhausted. So, this can be considered by this example. where this is the plot of stress versus number of cycles to failure. This is for a material which shows this type of curve, stress versus number of cycles to failure. If for example, the material at point sigma 1 and this is for the point sigma 2, where sigma 2 is lower when compared to sigma 1. Thereby, the number of cycles to failure is correspondingly higher for the case of sigma 2 and lower for the case of sigma 1. At points A and D, the life of the component is 100%. At these points, the life of the component is 100%, that is the points A and D. So, when a component, this component is subjected to a stress level of sigma 1 from point A to, from here this initial point, from point A to E up to here, the life of component is somewhat reduced because it has exposed to a stress level for so many cycles, that is for example 50 cycles, whereas the life of the component for this stress level is 100 cycles, 200 cycles. We assume that it is 200 cycles. So, how much of the life of the component is consumed, or it is 50 by 200, that is 1/4 of the life of the component is consumed when it is subjected to constant stress of sigma 1. So, this much of life is consumed, or this much of damage, 1/4 of the damage has taken place, where the total life of the sample is 200. At this point, at point D, the life of the component is completely exhausted at this point. If the component, same component, if it is stressed at sigma 1 and then if it is stressed at lower stress, that is sigma 2, the percentage of damage accumulated is equivalent to the percentage of damage accumulated in sigma 1. So, this is based on a linear damage accumulation rule. For one cycle, if the damage accumulated is some percent, when it is for another cycle, the damage accumulated is of the same percentage. Component, it is subjected to the stress sigma 1 and then it is subjected to a lower stress of sigma 2, where if the component is subjected to sigma 2, the life of the component, it would be 400 cycles. At this point, the life of the component is exhausted, 400. So, now it has been subjected to about sigma 2, which is the lower stress when compared to sigma 1. So, the damage that is accumulated, it is about 100 cycles, with that of 400 is the total life. So, the percentage of damage that is accumulated is again 1/4 of the total life, that is 100 by 400 is again 1/4 of the total life of the component. So, the percentage of damage accumulated when it is stressed at one value of stress is equivalent to the percentage of damage accumulated when it is stressed to another stress level, that is sigma 2. That means each cycle contributes to same percentage of damage accumulation at the specified stress level. So, in the case of sigma 1, when it is stressed at this point of stress, that is sigma 1, the damage accumulated or the life of the component that is consumed is 1/4. When the stress is lowered, then 1/4 of the life of the sample specimen is consumed. The damage accumulated, percentage of damage accumulated when it is stressed at sigma 1 is equivalent to the percentage of damage accumulated at sigma 2. So, this cumulative damage rule, which is given by Palgrim Minor, it assumes that total life of a component can be predicted by considering a series of sum of the percentages of life consumed, by considering the sum of the percentages of life consumed at specific stress levels. It is given by small n1 by capital N1 plus n2 by n2 and so on. So, this is equal to sigma cumulative damage rule. It assumes that the total life of a component can be predicted by considering the sum of the percentages of life consumed at specific stress levels, which is given by N1 by capital N1 plus N2 by N2 and so on, Nk by Nk is equal to 1. So, this is equal to sigma I is equal to j, where j is equal to k, small ni by capital Nj is equal to 1, where this N1, N2, N3, small n1, N2, N3 and Nk, they represent the number of cycles that are exposed at specific stress levels, and capital N1, N2, it represents the number of cycles to failure. This is the number of cycles to failure for the same stress, and small n1 is the number of cycles where the component it is subjected to, number of cycles the component is subjected to for the same stress. That is, from this example, for the case of sigma 1, that is the same value of stress, the life of the component is 200, that is capital N is equal to 200, but the component it is subjected to only 50 cycles. So, the life of the component consumed is about 1/4 of the life of the sample is consumed. So, small n1 is equal to 50 for the specific value of sigma 1 for the same value of stress, n2 and capital N2 for different value of stress. For example, sigma 2, the life of the component is 100, and if it is exposed to certain number of cycles, how much of damage has accumulated for that number of cycles. So, this is equal to 1. That means the damage accumulates in a linear way. The percentage of damage accumulated for one cycle is equivalent to the percentage of damage accumulated in the other cycle. But this cumulative damage rule, Minor's rule, do not consider the effects of overstress and understress. It does not consider the effects of overstress and understress. Overstress means if initially the component is subjected to high value of stress and then the component is stressed at a lower value, the life of the component will decrease because already some damage has taken place at that overstress level. Initially the component is subjected to higher value of stress, and then again if it is tested at lower value of stress, the life will be decreased because at that high value of stress some damage has already taken place. And understressing means initially if the component, if it is tested at lower value of stress, very low value of stress, and again if it is tested at high value of stress, the life of the component will increase. Why? Because at such low value of stress, the material undergoes strain hardening, and when this same material it is subjected to high value of stress, the material will show an increase in fatigue life because initially it has exposed to a low value of stress. So, these effects, they are not taken into account in this Minor's rule, overstressing and understressing. Now, the effect of various metallurgical variables as well as some of the factors to increase the fatigue life of the material. So, coming to the initial, the metallurgical variable, metallurgical factors that can improve the fatigue life of the material. Fatigue strength, there is some correlation between the fatigue strength and that of the ultimate tensile strength. in the case of tension test. A higher strength material shows better fatigue resistance, but this is not generally with all the cases, because as strength of that material increases, sensitivity to environment increases, as well as fracture toughness will decrease. For the case of steels, to around 40 HRC, Rockwell hardness number, tested on C scale, using C scale, the fatigue strength increase with increase in ultimate tensile strength. There is a ratio known as fatigue ratio, which is the ratio of fatigue life to that of tensile strength. So fatigue strength is about 50% to that of the ultimate tensile strength for the case of steels, but this is only an approximation, as well as this is only for the case of specimens which are very smooth, which do not contain any notches, and which are tested at zero mean stress. When the conditions vary, the same approximation does not hold. Moreover, fatigue properties, they are more sensitive, they are more structure sensitive when compared to the tensile properties. For example, if by the strengthening mechanism, by the precipitation hardening mechanism, the yield strength of the material increases, proportionately fatigue strength does not increase. It depends to a greater extent upon the structure, microstructure, because it is more sensitive, fatigue strength is more sensitive to structure when compared to that of tensile properties. So stacking fault energy, which controls the fatigue strength, this is one of the variable, metallurgical variable, which controls the fatigue strength of the material. Materials which has a low stacking fault energy, the difficulty to cross slip is more when compared to materials with high stacking fault energy. High stacking fault materials, they can undergo cross slip, that means the dislocations can cross slip very easily when compared to the low stacking fault energy metals. So fatigue strength is proportional to the difficulty of dislocations to cross slip. The difficulty to cross slip is more, fatigue strength is more. And moreover, in the case of high stacking fault energy materials, they undergo cross slip easily, as well as the slip is known as the wavy slip, whereas for the case of low stacking fault energy metals, where the cross slip is very difficult, dislocations are tend to move in a planar fashion. So the slip is known as planar slip. So this can be simply given as stacking fault energy, low stacking fault energy metals, difficult to cross slip, and then the slip is planar, where the fatigue resistance is high. And for the case of high stacking fault energy metals, it is easy to cross slip and they undergo wavy slip, which lowers the fatigue strength, and this increases the fatigue strength. So stacking fault energy is one of the variable, metallurgical variable, that controls that affects the fatigue strength. But by using this variable, one cannot increase the fatigue strength to a greater extent. There are only limited ways by which one can increase the fatigue strength by controlling the stacking fault energy. Moreover, with respect to grain size, fatigue strength is proportional to d to the power of minus half. Fine grain size material, they show better fatigue strength when compared to coarse grain size materials. But this is for the case of low stacking fault energy metals which do not develop a cellular structure. So this effect can be seen only for the case of low stacking fault energy metals which cannot develop this cellular structure. Whereas for the case of high stacking fault energy metals, they develop this cellular structure. So this cellular structure, they restricts the crack propagation. So the grain size, the effect of grain size is masked for the case of high stacking fault energy metals. Another variable that can be considered that affects the fatigue life of the specimen is roughness, surface roughness. Fatigue crack initiation takes place at the free surface, external surface. So if the surface is rough, this rough surface, it acts as stress concentrator, thereby crack nucleation initiation takes place very easily at this rough surface. So rough surface which is induced mainly during the manufacturing processes, so that leads to lower the fatigue life of the specimen. So surface of the specimen should be very smooth. Roughness lowers the fatigue life of the specimen. Next is by surface hardening methods. By hardening some of the surface hardening methods like carburizing, nitriding, these hardening methods, carburizing and nitriding, these hardening methods which harden the surface, apart from hardening the surface, they also induce residual compressive stresses. This residual compressive stresses, they are beneficial in increasing the fatigue life of the material. So these surface hardening methods, they increase the fatigue life of the material, they increase the fatigue strength of the material. Then one can also induce residual compressive stresses on the surface by means of surface rolling using contoured rollers, as well as by short peening. Short peening is a method which uses of fine steel shots, fine steel balls, fine steel shots, which are subjected at very high velocities over the surface of the component, which are shot at high velocities on the surface of the component. So this induces residual compressive stresses on the component. So one can measure the amount of this residual compressive stress by testing the residual deformation of these fine shots. And this residual compressive stresses should not increase beyond the yield stress. It should always be much lower than that of the yield stress. So by inducing residual compressive stresses either by short peening or by means of surface rolling using contoured rollers, one can induce this residual compressive stresses which increases the fatigue life, whereas compressive tensile stresses, it lowers the fatigue life of the material. So, these are some of the variables which increase the fatigue life of the material. Temperature is also having an effect. So, this we shall discuss in the environmental effects of failure, environmental effects of fatigue. In the environmental effects, we have the corrosion, environmental effects of environment on fatigue. We have first one is corrosion fatigue. Second one is temperature. That is, with increase in temperature, the fatigue life decreases, fatigue strength of the material decreases. With when the temperature is low, fatigue strength is high. And there is no evidence of any changes in the fatigue behavior when it is tested at very low temperatures. That means at this dBTT, ductile brittle transition temperature, there is no changes in the case of fatigue strength, no changes in the fatigue behavior. Then the third is thermal fatigue. Thermal fatigue, it is seen mainly the components which are subjected to very high temperatures. When there are certain variations in the temperatures, as we have discussed in the case of strain controlled fatigue, due to temperature variations, thermal stresses are induced in the material, and the material cannot freely expand or contract, that induces thermal stresses. Thereby the stresses are from the thermal origin. Material is subjected to thermal fatigue. If the failure occurs due to this repeated thermal cycling, then it is called thermal fatigue. If failure occurs upon one thermal cycle, then it is called thermal shock. Thermal shock means the material fails due to very rapid temperature change for one thermal cycle, it is called thermal shock. But if the failure occurs due to repeated thermal cycling, then it is called thermal fatigue. So, the stresses that are induced due to this temperature variations, it is given by this equation, delta sigma approximately equal to alpha, that is the coefficient of thermal expansion, E the Young's modulus, and delta T. Delta T is the variations in temperature. If the variations in temperature is very, very large, coefficient of thermal expansion of the material is very large, Young's modulus of the material is very large, the stresses that are developed in the material is also very large, and the material is subjected to this thermal fatigue failure. So, for a material to have good resistance to thermal fatigue, it should have a high fatigue strength and it should have a low thermal conductivity. It should have a high thermal conductivity and it should have a low coefficient of thermal expansion and low Young's modulus. So, if this ratio, if this is very high, this factor is very high, then resistance to thermal fatigue is also very high. High fatigue strength, high conductivity is preferred, low coefficient of thermal expansion and low Young's modulus results in better thermal fatigue resistance. Coming to the corrosion fatigue, simultaneous action of both corrosion and cyclic loading leads to corrosion fatigue failures. That means, if there is a simultaneous action of corrosive environment as well as the component is subjected to cyclic loading, So, failure occurs, that is known as corrosion fatigue failure. When a component it is tested in air, when a component which shows a definite or true endurance limit, for the case of mild steel for example, some components which shows this type of fatigue life, a true fatigue life, when it is tested in air, and if the same component, if it is tested in an corrosive environment, then the endurance limit is not seen. So, simultaneous action of both corrosion and fatigue leads to failure, that is corrosion fatigue. So, even though if fatigue is not present, initially there is a corrosive environment. So, because of the corrosion, pits are developed on the surface of the component. Pitting takes place due to corrosion. These pits, they act as stress concentrators, and fatigue crack initiation takes place at these pits if the component is subjected to cyclic loads. So, the failure that occurs is known as corrosion fatigue. So, in order to combat this corrosion fatigue, in the case of for a very aggressive environment, initial preference has to be given for a more corrosion resistant material than that of high fatigue strength material. So, for the case of an application in that of aggressive corrosive environment, high corrosion resistance material is preferred when compared to the fatigue properties. Coatings also can be given which protect the surface of the component from this aggressive environments, corrosive environment. So, these coatings, if they are ruptured because of the cyclic loading, again corrosion takes place and corrosion fatigue failure results. So, in the case of corrosion and fatigue, the reduction in life of the material decreases to a greater extent when compared to corrosion alone or when compared to fatigue alone. And with respect to temperatures, higher the temperature, lower is the fatigue strength of that material. But to this variable, temperature variable, that is with increase in temperature, the fatigue strength of the material decreases, fatigue strength decreases. An exception to this is mild steel, which shows an increase in fatigue strength, with increase in temperature, that is due to strain aging, which takes place in the temperature of about 205 degrees centigrade to about 300 degrees centigrade. So, within this temperature region, strain aging takes place, which increases the fatigue strength. So, generally we said that this is the general case, increase in temperature lowers the fatigue strength of the material, but exception to this is mild steel, which shows an increase in fatigue strength in this temperature range. And moreover, short peening, which is effective at room temperature, but at elevated temperature this is not effective, that is inducing residual compressive stresses on the surface of the components by short peening. This is not effective when the temperatures are very high. And moreover, this short peening method, which increases the fatigue life of the component, it is more beneficial for the case of high cycle fatigue when compared to high strain low cycle fatigue. Because of large plastic strains, they mask this compressive residual stresses, which is known as fading of residual stresses. So, these are some of the environmental effects on fatigue. And moreover, the endurance limit which is seen for the materials like mild steel, that is, which shows a true fatigue limit below which the stress below which the material can undergo any infinite number of cycles, but it does not fail even though it is exposed to any number of cycles. So, this can be attributed, the reason why it shows a true fatigue limit, it can be attributed due to the presence of interstitial elements. This is for the case of pure metal, this is stress versus N curve for the case of pure metal, this is for the case of solid solution, where the curve is above and it shifts to the right due to the presence of solid solution elements, and this is for the case of pure metal. And for the case of, this is for the case of interstitials present, which results in strain aging, and for increased or enhanced strain aging, this is the curve. This is for increase or enhanced in strain aging for the same material, where the curve is well above, and this endurance limit, it is endurance limit for the case of this material for the enhanced strain aging, that is increase in interstitials. It is to the left of this curve. Endurance limit is still higher as well as left of this curve, interstitials. So, this is for the case of pure metal, solid solution, and interstitials due to the strain aging behavior that takes place, and due to enhanced strain aging, the endurance limit is still higher and it is towards the left of this curve. Pawan, Monday, 3 o'clock.